Let's find the equation of motion for a pendulum. So this is going to be our first example where we are looking at the kinetics of a problem, right? We're going to be concerned with the forces. Before we were just looking at the kinematics, which was just position, velocity, acceleration. Now we're going to be applying some of Newton's laws. So I like to do the pendulum problem because, everybody has a pretty good idea of how a pendulum should behave, and it's a pretty good first example. All right, so let's set up the problem. We have this rigid, massless link that goes from O to P, point P, our mass P at the end of the pendulum. This is a point mass. It doesn't have any inertia, it's just a point. We have our inertial frame here, and this is absolutely fixed, right? It is non-accelerating. We have EX pointing straight down, EY pointing off to the right, and then EZ is EX crossed with EY. Next, we have our green basis here, which is fixed in frame P, P for pendulum, and ER points from O, from hinge point O, to our point P. So this is the direction of ER, always points like that. EZ is going to be out of the page as well, right? So green EZ is going to be equal to red EZ. And then E theta is going to be EZ crossed with ER. We'll give you E theta. It's always going to be perpendicular to the link. And we have gravity, the force of gravity, which acts on our mass here, point P. All right, so how do we even start finding this equation of motion? Well, we start with the kinematics, right? So we do what we've been doing. First, let's find our position vector. So to find a position vector, we just need to draw a vector from it could be any inertially fixed point, right? I'm going to pick point O just because that's what I have written there, right? I could have done an inertially fixed point here, and then drawn a vector from here to here, and then here to here. It doesn't matter. It does not matter. We're going to pick point O as our inertially fixed point, and we're going to say, how do we get from O to P? Well, we travel a distance of L. We travel a distance of L in the ER direction. And that's it. We did it. That's our position vector of point P, LER. Now we want to find the velocity of point P. The velocity of point P. And just keep in the back of your mind, we're doing all this because we need to find the acceleration of point P so that we can apply Newton's second law, which is F equals ma. We're trying to find A right now. So to find the velocity, we take the time derivative of the position vector. So we're just taking this here and plugging it right in to our derivative. And then we can apply the product rule, right? So the product rule is derivative of the first times the second plus the first times the derivative of the second. Okay? L is a constant, right? It's the length of the pendulum is not changing with time. It's constant. So the derivative of a constant is 0. So this whole term goes to 0. So we're left with this right here, which is this. L times ddt of ER. So we have to find the derivative of this unit vector. Well, we've done a lot of examples like this, and we did a whole video deriving this result. And we know that the derivative of a unit vector is equal to the absolute angular velocity of the frame crossed with the vector itself, right? So what's the absolute angular velocity of frame P in frame G? Well, how is frame P rotating with respect to ground? Well, it's rotating at a rate of theta dot, right? Because to get from our inertial frame to the green frame, all we do is a 3 rotations. So we're rotating about the z-axis by theta, and we're rotating at a rate of theta dot, right? The time derivative of theta dot. So this term here is just theta dot. And we're rotating about the EZ direction, theta dot EZ, and then we cross with ER. So what is theta dot ez crossed with er? That's equal to theta dot e theta. So d dt of er is equal to theta dot e theta, which tells us that, we can plug this in here, that the velocity of our particle is equal to L theta dot e theta. So that's our velocity. And now we're going to rinse and repeat. We're going to do the exact same thing for the acceleration. So we're going to take the derivative. We know that acceleration is equal to the time derivative of velocity. So we're going to take this guy, plug it right in for velocity. We'll get this. I'm going to take out L because we already said that it's a constant. You can take constants out of derivatives. So we have L times the derivative of theta dot e theta. And when we do the product rule here, we get L times the quantity, derivative of the first times the second plus the first times the derivative of the second. We're going to need this term here, d dt of e theta. Well, we can do the exact same thing we did up here for er. So we can do d dt of e theta is equal to the absolute angular velocity of frame p, which we said was theta dot ez. And then we cross it with the vector itself, crossed with e theta. Theta dot ez crossed with e theta is going to be negative theta dot er. Ez crossed with e theta is negative er. And so we can plug this in right here. And then we also know that, d dt of theta dot, that's just going to be theta double dot. So after we plug that in, you'll see we have theta double dot was this times e theta plus theta dot. And then we're plugging this guy in right here to get negative theta dot er. And if we do the multiplication for that and distribute the L, then we end up with the acceleration is equal to negative L theta dot squared er plus L theta double dot e theta. This is our acceleration of point P. So now we're going to go on to the kinetics. Kinetics always start the same way. We always first draw our free body diagram, and all a free body diagram is all the forces and moments acting on the system. A good way to kind of draw your free body diagrams is you draw a force for anything that restricts translational movement, and you draw a torque for anything that resists a rotation. For a 2D example, this is our free body diagram for a particle, where we have there's a force acting in the negative ER direction, and that is the reaction force of the arm on the particle. That keeps the particle from flying away off to infinity. And then we also have the force of gravity, which just acts purely in the EX direction. Gravity is acting in the EX direction. Right? Now you might be asking, Brian, how do you know that there's only this, oh my God, what's happening with the laser pointer? How do you know there's only a force in the ER direction? Why isn't there also a force in the E theta and EZ direction? And also, how do you know the force is acting in this direction? Couldn't it be acting in this direction? Well, the force that you put here, it doesn't matter what direction you put it in, because as you go through the math, the signs will fall out in the equations and they'll resolve themselves. Now, as far as the question, what about the E theta and EZ direction? How do you know there's not forces in those directions? I'm going to show you that at the end of this problem. Just for now, take it that this is the free body diagram. Okay, so the resultant force acting on the particles is the sum of all of the forces acting on the particle. Wow, great. That was kind of a useless note. But the total force F is equal to this force here, negative FRER, right there, plus mgex. Plus mgex. That's our force of gravity. Let's get this into the same basis, right? Because we have it in the green basis and we have the gravity term in the red basis. So we already kind of said this, but to get from the red basis to the green basis, we rotate the red basis by an angle of theta, and we're rotating about the EZ axis, right? About the 3 axis. So this is a fundamental 3 rotation. So this is where we were This is where we were going. And this is a fundamental 3 rotation by angle theta. That's it. And remember, you can take the transpose of this matrix in here where rows become columns, columns becomes rows. And then we can swap these guys. Right? So this is our direction cosine matrix to get the red basis in terms of the green basis. So now we can rewrite EX. What is EX equal to now? EX is equal to cosine theta ER minus sine theta E theta plus 0 EZ. And if we do that, all I'm doing is taking this that I just said and plugging it in for EX, right? So we have cosine theta ER minus sine theta E theta minus sine theta E theta. So that's EX in the green basis. So now we have our resultant force all in the green basis. We can combine terms. We can see we have an ER here and an ER term here. So we bring that into one term. Mg cosine theta minus FR, quantity times ER, minus mg sine theta E theta. Okay, so that's our resultant force. And now we get to apply Newton's second law. F equals ma. We just found F. We just found A. We know m. M is just the mass of the particle. Now we plug in. So this, all I'm doing is copying and pasting this guy right here. That's F. And then this right here is A. And I'm just going to show you real quick. We found that right here. That's A. And then we multiply A times M. I sometimes forget this M. Don't forget the M. But we're doing M times A. I'm just distributing the M for this next step. So just distributed the M. And you can see that we have an unknown in here. We don't know what FR is. That's fine. Let's get rid of it. Let's just get rid of it. How do we get rid of it? Well, we know that it's in the ER component. So what if we just dot this entire thing by E theta, right? What's ER dotted with E theta? ER dotted with E theta is 0. There's nothing wrong with dotting both sides of an equation by theta. That's completely fine, You can add 1 to both sides of an equation, it's the same thing. You can subtract 1 from both sides of the equation, it's the same thing, right? So we're going to dot both sides of the equation by the same thing. It's going to be fine. So we're going to dot both sides of the equation by E theta. And when we do that, you can see that's what we've written right here. We're dotting the left side by E theta, and we're dotting the right side by E theta. And when we distribute that, it's going to be ER dotted with E theta. That's going to be equal to 0. And you can see that killed that FR term. E theta dotted with E theta is just 1. E theta dotted with ER, again, 0. E theta dotted with E theta is 1. So now what are we left with? We're left with this term, and we're left with this term. So negative mg sine theta equals L theta dot, or ml theta dot. We can cancel m on both sides, and then we're left with, drum roll, the differential equation of motion. We did it. So the differential equation of motion for a pendulum with a rigid massless link is L theta dot times L theta dot plus G sine theta equals 0. That's it. All right, so going back to that resultant force thing with F theta and Fz, how did I know that those are 0 and non-existent? There's only a force in the FR. Well, let's pretend that those forces did exist, right? Just pretend that they're there then. Fine, nothing wrong with that. Then applying Newton's second law would yield, we're going to do F equals ma the same way. And this time we're going to add in, this is the same as we had before. Now we're going to add in F theta minus mg sine theta E theta. We're adding in, we don't know what it is. It's an unknown. It's F theta. It's in the theta direction, the E theta direction. And we're also adding Fz in the EZ direction. And then this is the same ma that we had above, right? So all we did was just pretended that there are forces F theta and Fz, right? Well, same thing. Let's do the same thing. Now we can solve for FR. And we're doing the same principle, right? We're going to dot with the ER component. And when we dot with ER, it's going to kill this term, it's going to kill this term, it's going to kill this term, right? So we're only going to be left with this and this. And then you can solve for FR, right? So that's what this is right here. After we do the dot product, we end up with FR. This is the value of FR. Now let's do the same thing. We're going to dot with the E theta component. When we dot with the E theta component, this term goes away, this term goes away, this term goes away, right? E theta dot with E theta is 1, E theta dot with E theta is 1, right? So we're only left with this and this right here. We can solve for F theta, and F theta is going to give us this expression. And what we'll find when we go over to the Python script that solves this differential equation of motion we just found, we'll find that this here is 0. This quantity here is 0. It's not immediately obvious the way we have it written right now, but we'll find that when we solve for F theta, it is going to be 0 because there is no F theta component to the force, the reaction force. And finally, EZ is the easy one to see because there is no EZ on this right-hand side of the MA part of the equation. There is no EZ component. So when you dot with EZ, this goes away, this goes away, this goes away, this goes away. So all we end up with is FZ equals 0. FZ equals 0. So that one's the easiest one to see. I have this little note down here. You could also prove that F theta equals 0 using conservation of angular momentum. We just haven't covered that topic yet, but if you use that approach, then it will show you pretty straightforward F theta equals 0. But we're going to stick with what we know so far, and let's go over to the Python script and see our animations for the pendulum, and also prove to ourselves that F theta is indeed 0.
So here we are in the Python script, and what this script does is it lets you define a whole bunch of different pendulums, give them properties like mass, how strong the gravity is, the length of the link, the pendulum link itself, and then it will animate those results. It will plot the angular displacement versus time, and it will also solve for the reaction forces that we were looking at before, that FR, F theta, FZ. The purpose of this video isn't really to show you how to solve differential equations of motion in Python, so that'll be a different video. But I will go through the script briefly just to kind of talk through it. So each pendulum is going to be a class by itself, and when you instantiate the pendulum class, you can give it a bunch of different parameters, like I said. So you can do gravity, mass, length. You define its initial conditions, how long the simulation runs for, and the time step. Right here is where we actually solve like the differential equation of motion, or this is the model that is solved. And right here is the differential equation of motion that we solved for already, right? Where Q dot, Q is theta dot. So Q is theta dot, Q dot is theta double dot. So theta double dot is equal to negative gravity divided by L times sine of theta, right? And that's just solving for theta double dot from our differential equation of motion we already found. Right here, solve, this method solve. This is what actually solves that model up there. And Z naught, this is our initial conditions. Since we're solving for theta double dot, we need initial conditions for theta and theta dot, right? So where is the pendulum starting and what is its initial velocity, angular velocity? So that's what we're doing here. This solves at each time step, which we call T-span. It solves that model. This method here plots the forces that we were talking about, FR, F theta, FZ. And you can see that right here, FR is equal to the equation we found in our derivation. F theta, same thing. And then FZ, there is no equation for FZ. It was just 0, like we said. There is nothing to set FZ equal to. So we're going to plot these and see what those give us. Here, if you don't know how to kind of edit this class or any of this code or anything, this is the only part you're going to really edit. And I'll show you how to edit it, add pendulums and remove pendulums. All you do is say I wanted to add a pendulum 6, a 6th pendulum here. You can just copy this. You can paste it. You can change these parameters to whatever you want them to be. And then we'll make sure you change the name of it. So we're going to call this pendulum 6, pendulum 6. And then you throw it onto our list containing all of our pendulum objects. So pendulum 6. That's it. Okay? So you can add as many pendulums as you want, remove as many pendulums as you want. Do whatever you want. You can see our initial condition is it's going to start at 45 degrees. It's going to start at 0 degrees per second. All of the gravity terms are going to be the same. All the masses are the same. The only thing changing between all these 5 pendulums are the lengths. So the first pendulum is half a meter. This one is 1 meter, 1.5 meters, 2 meters, 2.5 meters. Then down here, this plots the angular position of all the pendulums. Going down a little further, I won't go through this. It's a little involved, but this is the code for the animation that creates the animation of all the pendulums moving. And this Python script will be available on our GitHub. So just there'll be a link in the description. Go there. You can play with the code as much as you want. And then this plots the forces. Okay, so let's go ahead and run this. Remember, the only difference is the lengths. You know, the masses are the same, the gravities are the same. The lengths of the pendulums are the only thing that's different in this this code. Okay, so I think it should be done. Yes. All right, so here is the first chart it will do. This is the angular position in degrees for all of the pendulums that we plotted, right? And you can see the legends right here. So blue is pendulum 1, orange is 2, green 3, red 4, purple 5. You can see as the length of the link increases, the period increases, right? So the period here is, what does that look like? 1.4 seconds for half a meter length pendulum. And then, you know, we increased to 1 meter. So let's see, pendulum 2. Pendulum 2, the period increased to 2.1 seconds. So just something to note, you know, decreased length results in increased frequency. Something interesting. We'll just leave it at that for right now. Here's the actual animation. It runs a little faster if you leave it smaller. But here's the animation. We have the time showing it, and you can see this blue one is going back and forth faster than the longer ones, right? So the frequency is higher for the smaller length links. Very cool. Okay, so now let's look at the forces, those reaction forces that we were talking about. So this is for pendulum 1. This is the reaction forces for pendulum 1. And you can see we have FR. FR is oscillating back and forth. And would you look at that? F theta and Fz are 0. Okay, so that proves there is only one force, one direction component of force, and it was the FR component, right? The other two are equal to 0. You may be saying, Brian, you're lying. I don't believe you. All right, well, I proved it to myself again in OpenModelica. So here's the OpenModelica model, and you can see it's just a regular old Revolute with a link and a point mass. And the length of the link is 0.5, and the mass is 2 kilograms. And so if we go ahead and run this, we'll get a nice animation, 3D figure thing here, and it shows our reference frames. And you can see this red one is our inertial frame where X is pointing straight down, Y is pointing off to the right, and then X crossed with Y is Z, which is coming out of the page. This is our reference frame P, where this was the E sub R direction, pointing from O to P, E sub R. E sub Z is pointing out of the page, same direction as the inertial E sub Z direction, and then E sub theta, which is the green Y here, but E sub theta is Z crossed with X gives you E sub theta. Oops. And we can go ahead and run this animation if I can line this guy up. And if we run it, we'll see it's just a pendulum going back and forth. Great. And if we look at the forces, we can go over to the Revolute, frame B, forces, plot these guys. Let me make the lines a little thicker so You can see them. And there you go. So we can see that this red one, this is the X component, or the ER component. The blue is the E sub theta, and green is the E sub Z component. And you can see the E sub theta and E sub Z, those are 0 down here. And then E sub R is oscillating back and forth between 13.8 and 31.1. And if we look at our results from Python, 13.8 or something like that. It's hard to tell on Python, up to 31 point, around 31. They're the same thing. They're identical. So, yeah, there we go. We just proved this differential equation of motion in 2 different programs, which is fantastic. All right, that's it. That's all I got for this video. I'll see you in the next one. Bye.